Welcome to lecture 13 of electrical machines course. So in the last lecture, that is yesterday, we discussed about the autotransformer. In fact, we started the discussion of autotransformer. Uh, Already we have done a demonstrative problem on how to determine the parameters of a two-winding transformer. Then we talked about the autotransformers, and in that case we considered an ideal two-winding transformer, which is in fact connected in 4 different combinations to get the autotransformer, right? So let us do one problem here, then we'll go ahead with the non-ideal autotransformer. When we'll introduce the non-idealities in the in the form of winding resistance, leakage reactance, and also your core loss resistance and magnetizing reactance, then how the autotransformer will be represented and how we can analyze and find the performance of the autotransformer. So let us first do this problem. This problem is, so there is a two-winding transformer which is having a rating of 24 kVA, right? And the voltage rating is 2400 by 240 volt. That means it's a step-down transformer. It's a distribution transformer. In fact, all the distribution transformers, they are step-down in nature. And it is to be connected as an auto transformer. Okay. So we have already seen how we can connect the windings in series, and we can take the taps at different points to get different combinations of auto transformers. So for each possible combination, so there are 4 possible combinations, right? For each possible combination, determine the primary winding voltage, the secondary winding voltage, the ratio of transformation, that is AT, right? And the nominal rating of the autotransformer. So AT is nothing but it is V1A by V2A, right? So primary voltage of the autotransformer divided by the secondary voltage of the autotransformer. And finally, the nominal rating of the autotransformer is S. We have found SOA, right? So we need to find SOA, AT, then the primary winding voltage and secondary winding voltage. So now let us consider all the combinations separately. So one by one. First combination, this is in fact this combination is a step down combination where the input is V1 plus V2, or you can say E1 plus E2. Under ideal condition, E1 plus E2 will be equal to V1 plus V2. So V1 plus V2 by V2, right? This is a step down configuration, right? So I can name this configuration as V1 plus V2 by V2 step down configuration, okay? So now let us analyze this. So your V1A is nothing but E1 plus E2, right? Or I can say V1 plus V2. And V2A is nothing but it is equal to E2 or else V2, right? So easily the voltage is given, the rated voltage is given for this transformer. Now I can find V1A will be equal to V1 plus V2, right? So that will be 2400 plus 240, that gives me 2640 volt, right? Similarly, V2A is nothing but it is equal to your V2 or E2, whatever you can write. Under ideal condition, E2 equal to V2. So it will be 240 volt. Then so the transformation ratio of the autotransformer will be V1A by V2A. So V1A by V2A, so that is nothing but 2640 by 240, that is equal to 11, right? So that is nothing but 1 plus A. So then if we'll find the nominal rating of the autotransformer in kVA, right? So then I have to multiply the voltage, output voltage into output current, rated current, right? So output voltage, rated voltage is V2A, that is 240 volt, and I2A. So I2A is that also will be equal to V1A equal to, so V1A into I1A, right? So output power equal to input power under ideal condition. So I can write V1A equal to V1A into I1A equal to V2A into I2A. And from this figure we can see I1A is nothing but it is equal to I1. So I1 is the rated current of the two winding transformer in the winding associated with E1. Okay. So that is I1A under rated condition I1A will be equal to I1 because this winding cannot bear current more than I1 because this winding is rated at I1 in case of two winding transformer and the same winding we are using for the auto transformer. So therefore the rated current through this winding will be I1 which is equal to I1A. Okay. So therefore I can write V1A into I1. So I1 I know, I1 is nothing but it is 24,000. So 24 kVA is 24,000 by 2400. That is equal to I1. That is equal to 10 ampere, right? So just by substituting here, V1A we found it is 2640 into I1 is 10 ampere. So it gives me 26,400 VA or 26.4 kVA. Okay, I hope it is clear. Now we'll go for another configuration which is which is a step-up transformer, and this configuration is known because E2 is the common winding here, right? N2 is common winding, so this configuration is known as V2 by V1 plus V2. Okay, so V2 by V1 plus V2 step-up configuration. Okay, step-up connection. So now under this condition we know V1A is equal to E2, right? V1A equal to E2 or equal to V2, and your V2A will be equal to E1 plus E2, which is nothing but V1 plus V2, right? So obviously if we'll see, this will give me V1A is equal to V2, that is equal to 240 volt, right? And V2A is equal to V1 plus V2, that is 2640 volt, right? Now if I'll find the transformation ratio of the transformer 80, that is nothing but equal to V1A by V2A. So V1A is nothing but 240 and V2A is 2640. Just dividing it, I'll find 0.091, right? So this is a step-up transformer, therefore the transformation ratio should be less than 1, so it is 0.091, right? And if I'll find the kVA rating of this transformer, similar way if I'll proceed, V2A into I2A will give me the output, and also it is equal to V1A into I1A. So this is I1A, right? So V2A into I2A. So here I2A is nothing but is equal to I1, right? Because you can see here the winding that is connected in the output circuit is N1, right? So the rated current of this winding is I1, right? So therefore I2A will be equal to I1 under rated condition. Okay. So therefore it will become 2640, that is equal to V2A, and I1 is 10 ampere, so it will give me 26,400 VA or 26.4 kVA. Okay. So now I'll go for another configuration, which is, you can see here below figure, it is a step down configuration, which is also known as V1 plus V2 upon V1. Okay, so this is a step down configuration, right? So V1 plus V2 by V1 step down connection or configuration, whatever you say. Now your V1A will be equal to V1 plus V2, right? So your V1A will be V1 plus V2, right? And V2A will be equal to V1. So V1 is nothing but 2400. So this becomes V1A becomes 2640 and V2A becomes 2400. Now if we'll find the transformation ratio V1A by V2A, it will nothing but it is equal to 2640 by 2400. It will give me 1.1, right? So now if I'll find the rating of the autotransformer in kVA, then I have to find V2A into I2A, which is equal to V1A into I1A. And here I1A is nothing but is equal to I2. Okay, here the winding associated with E2 is connected to the input circuit. So therefore I1A under rated condition I1A will be equal to I2. So therefore I can write here V1A into I2, right? So V1A I know 2640 and I2 if I'll find from the two winding transformer it is 24 kVA by 240, right? So it gives me 100 ampere. So I multiply 100 ampere, it will give me 264,000 volt ampere or 264 kVA. Now under this configuration, your rating of the transformer is increasing, right? Very huge to a huge amount, that is 264 kVA, right? So when it was used as used as two winding transformer, the rating was only 24 kVA. And there is a huge enhancement in the output of the autotransformer. It is 264 in this fashion, that is this connection is known as V1 plus V2 of 1 V1, right? Step down configuration. So this gives me the output of 264 kVA, right? Similarly, if we'll consider another step of configuration, that is V1 by V1 plus V2, this is a step of configuration. So under this step of configuration, if I'll find V1A which is equal to E1 or equal to V1, that is 2400 volt, and V2A will be equal to V1 plus V2, 2400 plus 240, 2640 volt. Now the transformation ratio AT will be 2400 by 2640. Okay, so that will give me 0.91. Okay, so now your output of the auto transformer will be V2A into I2A. So that is equal to V2A into I2. So I2A is nothing but is equal to I2. So therefore it becomes 2640 into 100. So that will give me 264 kVA. So for two configuration we are getting very high output power of the auto transformer. It is around 264 kVA, right? Okay. So we can see here for two configuration like V1 by V1 plus V2 step up configuration and V1 plus V2 by this configuration by V1 step down configuration. For these two configurations we are getting the output of the auto transformer with a very increased way, very enhanced manner, right? So we are getting a very enhanced output of the auto transformer. Okay, so up to this point we consider the ideal auto transformer. Now we'll consider or we'll introduce the non-idealities into the auto transformer. So non-idealities means, so these are the four configurations. So if we have a two winding transformer, okay, you have a two winding transformer. This is your two winding transformer, the core, and this is V1, V2, I1, I2, right? So then, sorry, I2. Then your then if this two winding transformer will be connected as autotransformer, then we will have four combinations. Already we talked about, we discussed, right? So these four configurations are V1 plus V2 by V2 step down connection, V2 by V1 plus V2 step up connection, right? And V1 plus V2 by V1 step down connection, and V1 by V1 plus V2 step up connection. And all these four combinations in fact gives the increased power output, right? And with different transformation ratio, right? So these configurations what we are seeing here, they're all under ideal condition because we are neglecting the resistances of the winding, leakage reactances of the windings, and also the core loss component and your magnetizing reactance, right? So now if we'll introduce those non-idealities like the winding resistance each of the winding resistances of each of the winding, and the leakage reactance in each of the winding, and also the core loss component, then core loss component and magnetizing reactance, then how this autotransformer will be represented and how it will look like. Okay, so let us see then one by one with one by one configuration. So this is under ideal condition when the two winding transformer is connected in V1 plus V2 by V2 step down connection, right? So under ideal condition, this autotransformer, that two winding transformer when connected as autotransformer will look like this, right? So ZLA is your load impedance. Now if I will introduce the non-idealities, that means the resistance and reactance in the each winding. That means I am introducing here the resistance and reactance. That means here R1 and X1, JX1, and in this winding obviously R2 and JX2, right? And now the question is how to introduce the core loss resistance and the magnetizing reactance, because you can see here here I cannot put a uh, parallel RL circuit here because this has to be in the one side of the transformer, either as side 1, N1 side or N2 side, right? So because I cannot draw in the N1 side because it is connected in series, and this side is giving a series connection of N1 and N2. So therefore I need to put at this side because this is a common winding and this is common to both input and output, and here I can put the parallel branch that represents the core loss component and the magnetizing component, right? So I can put here R2 and sorry RC2 and XM2, right? Okay, so this part, this RC2 and XM2 represents the core loss resistance and the magnetizing reactance, okay, at the secondary side. Okay, so now I can see then if this will represent it like this, then how the equivalent circuit in case of autotransformer will look like, we can see here, right? So this component which is in the secondary side, right, this can be referred to the primary side. So this parallel branch, if it will be referred to the primary side, then obviously I have to multiply AT square. Okay, so it will be AT square RC2, then JAT square XM2. Okay, so here JXM2. So it will be referred, when it is referred, AT square will be multiplied with RC2 and XM2. So this is how it is referred to the primary side now. And the other components are represented as it is R1, X1, JX1 with the N1 winding or E1 winding, right? And R2 and JX2 is with second winding or E2 winding, that winding associated with E2, right? So R1 X1 with the winding associated with E1, and R2 X2 is presented with the winding associated with E2, right? Now, with further simplification, if I'll simplify it further, what I can do here, this resistance and reactance, which is here, I can refer these two parameters to this side, right? So if I'll refer to this side, it will be multiplied with a square only, because you can see here for a two winding, like we are referring like like in case of two winding transformer, right? So now this will give me an equivalent resistance RE1 and XE1. So RE1 already we know, RE1 is R1 plus a square R2, and XE1 is X1 plus a square X2, right? So when I will refer these quantities, this circuit will be more it will be more simplified. And again, if I'll refer this quantity, this load, it will be multiplied with, because it will refer to the secondary side, it will be 80 square ZLA, and V2A will become 80 V2A, right? Because this is now in the secondary side, if I'll refer it to primary side, 80 will be multiplied with voltage and 80 square will be multiplied with ZL. And similarly, this current will be multiplied with divided by 80, right? Now we can see the more simplified figure, or we can say it in the approximation form, right? So in the approximation form, now we can see this circuit. So this will remain as it is in the primary side, which is connected with V1, which is connected in parallel to V1A, right? Okay. And this part, this winding will be referred to now to the secondary side. So this will become RE1. So RE1 is nothing but it is R1 plus a square R2, and your XE1 will become J of X1 plus a square X2. Okay. So now your current also referred to the primary side, so therefore it will become IPA will be equal to I2A by 80. Okay. And your voltage when referred to the primary side, it will become 80 V2A and 80 square ZLA. So load impedance when it is referred to the primary side, it is multiplied by 80 square ZLA. Okay. So this is how we can represent the autotransformer. This is your exact equivalent circuit, right? Exact equivalent circuit. And this is your approximate equivalent circuit. So it is further simplified, and the analysis with this kind of circuit will be more easier, right? Approximate equivalent circuit. Okay. Now this is for one configuration, that is V1 plus V2 by V2 step down configuration. Now we'll see another configuration. This is the configuration of V2 by V1 plus V2 step up configuration. So in this configuration, we can see that N2 is your common winding. So therefore, I can draw here the non-ideality of core loss component and magnetizing reactance in the common winding, right? So that will give me RC2, okay, and XM2, right? And here obviously I'll introduce the non-idealities of resistance and reactance in each of the winding, right? So then your exact equivalent circuit will look like this, right? Now it will become RC2 JXM2. This is your parallel branch which represents the coreless component and the magnetizing component, and your series resistance and reactances are represented in the respective windings R1 and X1, right? Okay, so and also R2 and X2. So this is your exact equivalent circuit. Okay, and if I'll represent this in the form of approximate equivalent circuit, what I need to do? So if I can, because this is your secondary circuit, and now if I want to refer it to primary side. So what I have to do? First I have to refer this R2 and X2 to this side. So this side is your secondary side of the autotransformer. Now the whole secondary side parameter will be referred to the primary side. That means after referring R2 X2, I will get this side RE1, that is R1 plus A square R2, sorry, and X1 will be X1 plus A square X2. Okay, so when I will refer this to this side, this RE1 and XE1 will be now in the secondary side of the autotransformer, right? So along, so how it will look like? It will look like this. So I'll plot it here. It will be like this part is your secondary side. Sorry. This is your load. Okay, sorry, this is your load. So now this will become RE1, this is XE1, and this is your ZLA V2A. So this part is your secondary side, this part is your primary side. Now if I'll refer this whole secondary quantities to the primary quantity, then I have to multiply with AT square. So, so if I'll refer RE1, XE1 and ZLA and V2A, all these quantities into the primary side, then I will multiply AT square with the RE1 and XE1 and ZLA and A with V2A, right? So that is what I can see here. Sorry, I can see here easily. So your RE1 and XE1 is multiplied with AT square, right? And AT square XE1. Again, your load impedance is also multiplied with AT square, because these all these quantities are now referred to the primary side. Okay, and your voltage, secondary side voltage, is multiplied with AT. Okay, now your current in the secondary side will be divided by AT, so that when it is referred to the primary side. Okay, okay. So this is for the configuration of V2 by V1 plus V2, right, for a step up type of connection. Now we'll see another step down configuration, which is V1 by V2 upon V1. Okay. In this connection, if we can see, so this E1 winding, or the winding associated with E1, is common to both primary and secondary side, right? So therefore now I can draw here the core loss resistance and your magnetizing reactance. Okay, so core loss resistance will be here RC1 and it is XM1. Okay, and similarly other resistances and reactances can be drawn in the respective windings. Okay, so here we can see because this is your secondary point, secondary side, so now I can refer it to primary side. So therefore your RC1 and XM1, when referred to the primary side, it is multiplied with 80 square, right? And other quantities have been represented as it is. Your R2, X2, they're associated with the N2 winding, and R1 and X1, they're associated with E1 winding, right? And obviously your V2A and ZLA will be there. So now this part is your secondary side. Okay, now how to refer this to primary side? Okay, so in order to refer to the primary side, what I need to do is, sorry, this part is your at the secondary side, this is in the primary side. Now I want to refer these quantities, these common winding quantities, into the primary side. So if I'll refer this, I have to divide this with with a square, right? So here if I'll bring R1 and X1 to the N2 side, then I have to, here I'll get RE2, that is equal to R2 plus R1 by a square, and your XE2 will become X2 plus X1 by a square. Okay. Now the whole quantity will be in the primary side. Whole parameter, all the parameters will be in the primary side except ZLA and VA2 or V2A. This can also be referred to the primary side just by multiplying AT square ZLA and AT V2A, right? And your I2A will be referred to the primary side just by dividing I2A by AT. I2 by, sorry, I2 by AT will give me IPA, right? Okay. So this is how we got here the expressions. Your parallel branch RC1 XM1 is referred to the primary side, that is multiplied with AT square RC1, AT square XM1, and your series equivalent parameters RE2 will be equal to here R2 plus R1 by a square, and XE2 will become X2 plus X1 by a square, and your ZLA will be multiplied with AT square when referred to primary side, and your V2A will also be multiplied with AT, and your current will be divided by AT. Okay, so this is your third configuration. Now we'll see the fourth configuration. Your fourth configuration is V1 by V1 plus V2 step up connection. So here in this case your common winding is N1. Okay, so therefore I can draw here the core loss resistance and the magnetizing reactance, right? So that is RC1 and XM1. Okay, so these two quantities are already there in the primary side, no need to refer, and all other parameters like R2 and JX2 I can mention here along with the winding R1 and JX1. Okay, so that will give me this kind of circuit. This is your exact equivalent circuit, right? Exact equivalent circuit. So in this circuit, we can see RC1 JXM1 and R2 JX2, R1 JX1. These are all transformer parameters. We can see here that this common winding is we need to refer to the secondary side because this common winding somehow referred to the some sides, either primary side or secondary side. It is already in the primary side completely. So therefore, if we'll refer it to the secondary side, so I can write it here. RE2 will be equal to R2 plus R1 by A square, and sorry, RE2 will be S R2 R1 by A square, and your XC2 will become X2 plus X1 by A square. Now the whole component, this RE2 and XC2, ZLA and V2A, all are in the secondary side of the autotransformer. Now, if I'll refer this RE2, XC2, ZLA, all these components to the primary side, then I have to multiply it with AT square. So therefore, your approximate equivalent circuit will look like this. So already RC1, XM1 there in the primary side, and if I'll refer this RE2 and XC2 to the primary side, I have to multiply with AT square. That will become AT square RE2. It will become JAT square XC2. Similarly, if I'll refer ZLA to the primary side, I have to multiply AT square. It will become AT square ZLA, and the voltage will become AT V2A, and the current will become obviously I2A by AT. So all these circuits what we have drawn till now, these are all representing the approximate equivalent circuit finally when the autotransformer is viewed from the primary side. Okay, so that means when a two-winding transformer is represented through represented as autotransformer, we'll have 4 different combinations, and for each combination we can draw the exact equivalent circuit, as well as we can also draw the approximate equivalent circuit. Okay. And using these equivalent circuits, we can analyze very easily the autotransformer performances. So in case of finding the performances of the autotransformer, we need to find the efficiency and the voltage regulation, right? So efficiency, we know it is the power output by power input into 100. This gives me percentage efficiency. So percentage voltage regulation is nothing but it will be your V2 V2A, sorry, V2 no load. You can say it as V2A no load minus V2A by V2A. This will give me into 100. This will give me a percentage voltage regulation, right? Okay, so by using these two formula, we can find the performance of the autotransformer. Okay, so both the circuit you can use. If the question is asked to use the exact equivalent circuit, you have to use the exact equivalent circuit to find the performance, or if it is asked, use the approximate equivalent circuit to find the performance, you have to use this kind of circuit, which is the approximate equivalent circuit. So now we'll do a problem which is in fact which considers the analysis with exact equivalent circuit. So when we'll consider the exact equivalent circuit and approximate equivalent circuit, almost the performance, the value of efficiency and voltage regulation, they're almost approximately same, right? So let us do this problem using the exact equivalent circuit. Okay. Now in this problem, we have a two-winding transformer which is having rating of 720 volt ampere. So this is your rating of the two-winding transformer, right? SO is 720 volt ampere. And the voltage rating is given here 360 by 120. That means your V1 is 360 and V2 is 120. Okay. So, so this two winding transformer has the following parameters, following constants. RH equal to 18.9 ohm, XH equal to 21.6 ohm, RL equal to 2.1 ohm, XL equal to 2.4 ohm, and your RCH is 8.64 kilo ohm and XMH is 6.84 kilo ohm. That means the coreless resistance in the high voltage side is 8.64 kilo ohm and the magnetizing reactance in the high voltage side is 6.84 kilo ohm. So now the transformer is connected as an autotransformer in this fashion, which has the input of 120 volt and 480 volt, right? That means it is a step-up transformer. So 120 volt is the input side. 120 volt winding will be connected to the input voltage, right? That means it will be the common winding, and 480 volt is your output volt, which is the combination of the 360 plus 120, right? So if the auto transformer delivers the full load at 0.707 power factor leading, so when the power factor is leading, it is 0.707, then determine its efficiency and voltage regulation. That means your load, the load connected at the output of the auto transformer is having a power factor of 0.707 leading. Okay. So now let us find the performance of the auto transformer by finding the efficiency and voltage regulation. So in this analysis, we'll consider the exact equivalent circuit for the analysis. Similarly, we can do this analysis using the approximate equivalent circuit as well. So now let us draw the auto transformer circuit. So before that, let us find the transformation ratio of the auto transformer. So the transformation ratio of the autotransformer will be 80, which will be equal to 120 by 480, right? The ratio of the primary side and secondary side voltage, that will give me 0.25. Okay. Now, the transformation ratio of the two winding transformer will be V1 by V2. This will be 360 by 120, that will be equal to 3. Okay. And if we'll find the core loss resistance at the low voltage winding and the magnetizing reactance at the low voltage winding, we need to divide it by A square. So it will become 960 ohm and 760 ohm respectively. Okay. Now let us draw the equivalent circuit. So here in the equivalent circuit, the core loss resistance and the magnetizing reactance, which is referred to the primary side, that if we'll draw, that will be RCL and XML. So it is drawn here. RCL is 960 ohm and XML is 760 ohm, right? Okay. And this is your winding of low voltage winding. So low voltage winding, the parameters are 2.1 ohm, RL and XL is 2.4 ohm, right? And the high voltage, for high voltage winding, this is the resistance, the high voltage winding RH, and this is your XH. Okay, so now your output voltage, rated output voltage is known, 480 volt. Let us consider this voltage as a reference phasor. This is V2A. Okay. And with respect to this phasor, we'll find all other phasor quantities. Now let us find I2A. So how I'll find I2A? I2A, if we'll find the this rated current in the high voltage side will be I2, that will be equal to the rated current of the auto transformer when the auto transformer is operating at full load, right? So I2A will be equal to I2. So that will be equal to how much? That will be equal to 720 by 360. It will give me 2 ampere, right? Okay, so now your I2A, the magnitude of I2A is 2 ampere. Now what will be the angle of I2? Because the load angle is given, load power factor is given 0.707. So your angle will become cos inverse of 0.707. So that will give me 45 degree. So it is mentioned that it is a leading power factor. So therefore your current in the output circuit, that is I2A, will lead the voltage V2A. That means your angle will be positive. That therefore your I2A now became 2 angle 45 degree. Okay. Now we found I2A, right? Now in order to find the efficiency, we know efficiency is PO by Pin. So PO, in order to find PO, I need to find the real part of V2A I2A star and real part of V1A I1A star, right? So V2A and I2A I know from this calculation, and V2A is given, right? Therefore I can find PO. But in order to find P in, I need to know V1A and I1A. So V1A is known to me. V1A is nothing but it is 120 volt. So V1A is 120 volt. Now I need to find I1A. So I1A will be how much? I1A will be equal to IPA plus I phi A, right? Okay. So how to find I phi A? I phi A is nothing but it will be, so your I phi A will be how much? It will be V1A by RCL. Okay. So therefore I need to know V1. So sorry. Yes, I need to know V1A. So V1A is not known to me. V1A I have to find. Sorry, V1A I have to find. So V1A is not known to me. So I cannot say V1A is 120. So V1A, in fact, the voltage across this circuit, right? So in fact, the EL is given to me. EL is 120 volt, right? EL is 120 volt. Okay, so now how to find V1A? So V1A is nothing but it is equal to EL plus I common, that is the current flowing in this winding, I common, let us say I common into RL plus JXL. Okay, that will give me V1A. So therefore I need to find I common. So in order to find I common, I must know IPA and I2A. So IPA will be how much? So IPA will be nothing but I2A by AT. So AT is given, AT is your 0.25 that we have calculated. So if we'll divide 2 by 0.25, it will become 8 ampere 45 degree, right? So now IPA I know and I2A I know. So I common will be how much? That is the current through this common winding will be IPA minus I2A, right? So if I'll subtract these two currents, it will be 645 degree, right? Okay. So now using this current, I can find V1A. So V1A is nothing but your EL plus I common I RL plus JXL, right? So now I can find, okay. So I can find now V1A. Okay. So this is how all derivations are given. You can see it, right? What I told now, it is given here. So this is your IPA become 845 degree. Then your I common became 645 degree, right? So your EH becomes how much? Sorry, your EL is also not given, right? So EL and EH, they are also not given. So uh, we have to find the EL and EH from this by applying KVL in this circuit. So you know EH equal to 3 EL. So EL is also not given, sorry. So we need to find EH and sorry EL using this applying the KVL in this circuit. So your EH is nothing but is equal to AEL. So A is 3EL, right? So now writing the KVL in this loop, so I can write 4EL, that is 3EL plus EL, that will give it 4EL, that will be equal to I2A RH plus JXH plus V2A, right, minus I common RL JXL. So by solving this, I can find EL. So EL will be here, it is mentioned, EL will be around 119.745, right? And the angle will be 4.57 degree. Okay. So after finding EL, then I can write this equation V1A. So V1A will be equal to EL plus I common RL plus JXL. So then substituting EL, I common RL, JXL, I'll find V1A. So now I can find V1A. So V1A is equal to EL plus I common into RL plus JXL. So after substituting the values, I am finding V1A around 121.513, 13.63 degree, right? So after finding V1A, I can find I phi A. So I phi A is nothing but ICA plus IMA. So ICA is V1A by RCL, that is 0.127, 13.63, and IMA is nothing but V1A by JXML. So that will give me 0.160 minus 76.37 degree. So by adding these two currents, ICA and IMA, I find I phi A. So now I can find I1A. So I1A will be nothing but I phi A plus IPA, right? So now I can find I1A, IPA plus I phi A. So that will give me 8.027, 43.56 degree. So now I can find PO and PN. So PO already I told you how to find, already the values are given. So it is coming around 678.82 watt, and PN also similar way if we'll proceed. So V1A is known, I1A is known from the calculation. So I can find the real part of V1A, I1A star. So it will give me 8.027 minus 43.56 degree. Okay, so now I can find the efficiency. So efficiency will be PO by PN into 100. It will give me 80.3%. Okay, so the efficiency now is becoming 80.3%, and your voltage regulation will be becoming, you can see, in order to find the voltage regulation, we must find the no load voltage across this, and full load voltage is known. So the no load voltage across the secondary side will be V1A by 80. So that will give me 486.056. So then your voltage regulation will become no load voltage minus full load voltage by full load voltage into 100. So that gave me 1.26%. So your voltage regulation is very good, but your efficiency is decreasing because of the copper loss in the manner of in the common winding, right? So we have seen the efficiency is decreasing, but because of the more loss, more copper loss, right? So your voltage regulation is improving, right? Okay, so we'll stop here, and your auto transformer is also completed. It is and now from next class onwards in the lecture 14 we'll talk about the three-phase transformers. So all this we have discussed only single-phase transformers, right? So we'll talk from next class onwards the three-phase transformers. Okay. So thank you very much.